Welcome guys. Yeah, so today we are going to talk about summation by part. So since we are in the episode of convergence, yeah, we already talked about the root test and retro test, and there are some few of them. There are some other topic in the series. Okay, so theorem. All right, so this is from the so now I will write the rootings theorem, the number for you guys, so that you can check. So given two series sequence, let's say an and bn, and then let's put this an to be ak, right? K from 0 to n, and I put a minus 1 to 0, and we have the following. We have suppose that you have p less than q, this is 0, and we have a and bn, n from p to q. Sum of this equals to an bn minus bn plus 1, and from p to q minus 1 plus aq bq minus ap minus 1 bp. Yeah, so this is the summation by part formula. Okay, yeah, let's prove. I think this is easy, right? So let's say we have this p to q, right? So let's write the first. Let's change this an to be an minus 1, right? Bn. Right, so you have this, and you can write down its two terms, an bn from p to q minus n equals p minus 1, q minus 1, an bn plus 1. Okay. And yeah, you see carefully this term is exactly this term, right? Because you can shrink this, you can get out of an, and then you will rest of this, you will additional aq bq minus the ap minus 1 and the bp. That's a proof. Okay. Yeah, so from this we can get another theorem, which is somehow people like to use. Okay, so suppose now let's say a unbounded bounded. So unbounded means what I'm saying is that an is bounded, and b is that if b is monotone, and c is that it goes to 0, then sigma a and b and converge. Okay, so to do this, we just need to make an absolute value of this, right? Since we know that in the code, all of these a and b and are just by default is a complex number, the real number. Okay, so we can just take the absolute value of it, right? So equals to p from q minus 1, an bn plus 1 plus aq bq minus ap minus 1 bp, right? Take an absolute value, right? So since it's bounded, right? So I can assume that all the an, so I can assume all the an, right, is bounded by m. Right, so I can take m out, right? So now it becomes p to q minus 1, bn minus bn plus 1, right? Plus bq minus bp. And obviously this is term will cancel, so finally the remainder is 2 and bp, right? And this is less or equal to 2 and bn, large n, right? Because let's say you pick up n such that p and q are all greater than n, right? You pick a fixed n, and this term can approach to 0 as n goes to infinity by our assumption C. Okay, and this is assumption A, and this is assumption B. Right, so from ABC we know that it converge. Okay, yeah. So this is theorem. I remember this is theorem has a name, but yeah, don't worry, I just forgot about the name. Okay, and another theorem which about partial sum is suppose that you have a sequence Cn satisfy the C1 less or equal to greater or equal to C2, greater or equal to C3, and keep going. And the B is that the C2 and minus 1 greater than 0, C2 and less or equal to 0. So this means that the one is positive, one is negative. So for example, this series, right? So the odd term is positive, the even term is negative. Odd term is positive, and the even term is negative. So there's a name called telescoping series. Telescoping series. So this theorem basically just the conversion of the telescoping series, and the third condition need to satisfy that Cn will goes to 0 as m goes to infinity. Okay, so once you have these, the summation Cn converge. Okay, so example is this, right? So this is typical example. It satisfied the absolute value decreasing, and the odd term is positive, even term is negative, and then you approach to 0. So this is famous Leibniz series, right? So you know that converge. Okay, so this is the telescoping series or alternating series. Yeah, so the theorem just say that this guy converge. Okay, so you can use this another example that you can check this. And this is long too, right? You know they converge. Okay, now there's a very beautiful results that you guys can see, can try what this is. Okay, I will not tell you. Proof. So the proof is easy, right? So let's take an to be the -1 to the I think n plus 1, and the bn just take it to be cn, and then from the previous results. Right, so previous results tell me that now an is bounded and the bn is approach to 0. So we know that a and bn converge, right? So in this case, just this, right? So this is just summation of cn, right? Because the odd term is positive, even term is negative. Okay. Yeah. Okay. Okay. So let's talk about. There are a lot of proof of alternating series. This is just the more elegant proof by first introducing the summation by part. Okay, so let's prove another theorem, which is a final theorem about summation by part, not integration by part. Okay, so suppose you have radius. Suppose that you get some series which the converged radius is 1. So it means that any z less than 1, then this summation C and absolute will converge. And suppose, I think this is theorem called Abel's theorem. Okay. So suppose C0 greater than C2, Okay, and so it's decreasing and as n goes to infinity. So once you have these two, and then sigma Cn converge at every point of C equals 1, except possibly Z equals to 1. So which tell you that if you have a radius, if you have a guy which converge radius 1 and is decreasing, then this series will converge every point on this circle. There's only one dangerous point, which is here, which is the 1, 0 point. Okay. Okay, so old trick, right? An equals to Zn, and Bn is Cn, right? So An is bounded, right? Because An is because I choose Z less or equal to 1, right? So An is bounded, and the Bn is always decreasing. Okay, so by the theorem, so we only need to check. Large An is bounded, not small An, right? Now large An is bounded. So in the previous one, large An is definitely bounded, right? Because An can at most 0 or 1. Okay, so let's see how to bound this An. So this is m from 0 to n z m, right? So this is easy to bound because this is 1 minus z, 1 minus z n plus 1, right? So people can control this, right? This is less or equal to 2 1 minus z, right? Because however, if z less or equal to 1, you can use the triangularity identity to make this 2. And so the only case that if z is not equals to 1, then this is okay, right? So which prove the result. Okay. Okay. So let's talk about another topic called absolute convergence. Okay. Still follow the routine. Okay. So definition. So if one say that if I say that sigma an converge absolutely, somehow sometimes I'm very easy. Absolutely, if only by definition, if only this guy, you take absolute value converge, right? So absolute convergence means that you take absolute value and it converge. Okay, so for example, 1 over, right? So example the first example is that any positive, or I should say any non-negative sigma an converge is the same as absolute converge, right? Because if the original an is non-negative, then take absolute value just non-negative is absolute converge. Okay. And another yeah. So this is the usual example, the definition. Okay. And if not, so if this guy converge but it's absolute do not converge, this is just not absolute converge. Okay, so the famous example is how we already write. You can use this. Right, so this is a famous 1 minus 1 to infinity. Right, so this guy converge by our telescoping theorem, right? By our telescoping theorem, you prove it's known too. And but if you take absolute value, you get n from 1 to infinity, 1 over n, right? So this guy will not converge. This is the P series. So we already proved it's diverge. So P series. Piece 1. Right. So that means this sequence is not the absolute converge. Okay. Okay. So there's only one theorem that I want to prove. Very easy. So theorem, if sigma an absolute converge, then if somebody which is take absolute converge, then original converge. Okay, so proof just one line. Okay, so proof by the inequality. If you take about the partial sum, let's say P to Q, and then you take absolute value is less or equal to you take absolute value. Okay, right? Since it's converged, since in our case, in a Euclidean space, that the Cauchy sequence is equivalent to converge. So if one can bound the partial sum from P to Q, then one can bound the partial sum from this, right? So proof is done. Okay, so because one can, since it converge, so this guy is Cauchy, you can control this, so you can control this. Sometimes I prove things. I can guarantee that the proof is 100% correct, but I'm just a little bit lazy. Okay, so yeah, I think that's the final thing. Next video we talk about the manipulation of the sequence and the famous rearrangement. Okay, so see you guys next videos.